Hi everyone. Today we're going to learn a little bit about algebra, precisely about factorization, and then after that we're going to try to solve some math problems, which will be Olympiad based and some other much trivial problems. So to start with, we'll be starting with some algebraic identities, factorizations, which I have already listed here. Some of you might be aware of them. So for example, um, the difference of two squares, x squared minus y squared equals to x minus y times x plus y. So this is an algebraic identity which you can prove by trying to expand this product right here. So for example, in this case, we have x minus y times x plus y. So when you try to expand the product, we use the distributivity product from one factor to the other. So it's x times x, which is x squared times x plus y, which is xy, then minus y times x is negative xy, and then minus y times y, it is minus y squared. So as you can see here, we have positive xy and negative xy, which cancel out to bring x squared minus y squared. Okay, so this is an algebraic identity. The first one. So for the second identity, we have x cubed minus y cubed equals to x minus y times x squared plus xy plus y squared. Okay, so how do we prove this? So we start with the algebraic product on the right hand side, then we show that it is exactly equal to the difference of two cubes. So you start with x minus y times x squared plus xy plus y squared. So again, when you expand this product, x times x squared, you get x cubed, x times xy, we get x squared y, x times y squared, we get x y squared. And then for the other part, minus y times x squared is minus yx squared, minus y times xy is minus x y squared, and minus y times y squared is minus y cubed. And so for this reason, we can see that the two terms x squared y and xy squared, and yx squared, they're the same product. So except their signs are different. This one is positive and the other one is negative. So they will cancel out in the sum. And the same goes for the expression xy squared and minus xy squared. So these two will cancel out. Same goes for these two. So what will remain in the sum is x cubed minus y cubed, which is what we wanted to prove here. So that is the second identity. For the third identity, we have x to the n minus y to the n equals to x minus y times this term here, which is of degree n minus 1. So in this case, n can be any positive integer. It could be 1, it could be 2, it could be 3, it could be any positive integer. Then this factorization will be true. So in this case, we can also try to prove this expression. So on the right hand side, we have x minus y times x to the n minus 1 plus x to the n minus 2 y, on and on until we get x y to the n minus 2 plus y from n minus 1. So when we try to expand this product, we expand it with x first. With x, we get x times x minus 1, it is x to the n. X times the second term is x to the n minus 3, sorry, n minus 1. times y plus, again, this is a continuous sum, so there could be several other terms in the middle, and then when you get to x times y to the n minus 2, we get x squared times y to the n minus 2 plus x times y to the n minus y, x to the n minus 1. Okay, so for the other terms, we multiply negative y with this whole second factor, and so for that reason, minus y times the first term, x to the n minus y, x to the n minus 1, it is x to the n minus 1 times y. For the second term, it is negative y times this term here, which will be negative x to the n minus 2 times y, and so this will go on until when we reach at, sorry, this one is minus, so all the terms are negative. Negative y times x times y to the n minus 2, for which the product will be x times y to the n minus 1 plus, sorry, the last term will be minus y power n, y power n, sorry. So for the second terms, they will all be negative, but as you can see, this term and this term, they have the same magnitude. They are both x power n minus 1 times y, except that here we have a positive term and here we have a negative term. The same goes for the next factor. For the next factor here, it will be x times the term that comes after here. So it will be x times x to the n minus 3 times y, which will be x to the n minus 2 times y, which is precisely the same magnitude of this one, except that they will be of different signs. So one is positive and the other one is negative. And the same goes for all the middle terms until we reach this last term on the upper row, which is the second last term on the lower row. And as before, the magnitude is the same, but they have different signs. So in this case, these terms will end up cancelling each other in the sum. So this cancels with this, and so the middle terms, all of them will end up cancelling one another. And at the end, we'll be left with x to the n and minus y to the n, which is what we wanted to show as our third identity. Okay, and as you can see, if we plug in x equals to 3 in this case, we get x power 3 minus y power 3 equals to x minus 1, x minus y, times x squared plus xy plus y squared, which is exactly our second identity here. So the third identity is a generalization of a second identity, because here n can be any positive integer. Okay, for the fourth identity, it is similar to the third identity, except we have a slight variation. So for the fourth identity, we have x to the n plus y to the n equals to this product here. So again, we'll start to expand the product and we'll show that there will be a lot of cancellation in the middle terms, and we will be left with only two terms. So, and in this case, it is important to know that n has to be an odd integer. So n can be equal to 1, 3, 5, 7, and so on. Only odd integers can satisfy this relationship. Okay, so in this case, we'll start to expand the product. We have x plus y times x to the n minus 1 minus x to the n minus 2 times y plus x to the n minus 3 times y squared minus on and on until we end up at x minus x times n to the y minus 2 plus y to the n minus 1. So as we can see, this second term is a little bit complicated, but it's not that complicated because as before, we keep on subtracting the power of x and we keep on adding the power of 2. But at the same time, we keep on alternating the sign of the terms. For example, here the sign is positive, in the second term the sign will be negative, and then we have a positive and then a negative, and so on. Now, because n is an odd integer, when we reach at x times y to the n minus 2, it will be a negative because the sign depends on the power of y. If the power of y is an odd integer, then it will be a minus. If the power of y is an even integer, for example here of 2, then it will be a plus. So by the time we reach the exponent of n minus 2, which is an odd integer, because n is odd, it will be a minus. And when we reach to n minus 1, it will be a plus. So it's that simple. And so when we try to expand the product by x from the first product, we'll get, x to the n minus x to the n minus 1 times y plus x to the n minus 2 times y squared minus so on. And then at this last term, we'll have x squared times y to the n minus 2, and then plus x times y to the n minus 1. Okay, and so when we go on to expanding for y, we have y times x to the n minus 1 will be a plus, and then minus x to the n minus 2 times y squared, and then plus y times this term here, so it will be x to the n minus 3 times y cubed, and then we have a minus, and the series will continue until we arrive at y times x times y to the n minus 2, which will be minus x times y to the n minus 1. And then finally we'll have y to the n. And so as you can see, in this expansion, there is a lot of cancellation which will be going on, as we have seen in the previous case. So in this case, you can compare this second term from the upper row and the first term from the lower row. We have y times x to the n, which is the same as x to the n times y, except we have a difference in sign. Here it will be a negative and here it will be a positive. So they will cancel each other in the sum. The same goes for the second terms. From this term and this term right here, they have the same magnitude except that the sign is different. And this will continue throughout the sum until we arrive at this last term in the upper row and the second last term from the lower row. Here we have a negative, and then here we have a positive, although the magnitude x times y to the n minus 1 is the same as the one above. So they will cancel throughout the entire sum. Yeah. The only terms which will remain in the end is x to the n plus y to the n, which is what we wanted to show. So, for example, if we plug in n equals to 3, then we will have x to the 3 plus y to the 3 has to be equal to x plus y, okay, x plus y, then plus the second term is x to the n minus 2. In this case, it will be x squared, and then minus x to the n minus 2, because n is 3, so it will be x and then times y. And then the third term here, which will apparently be our last term, because n is 3, it will be y squared. So for n equals to 3, we have this identity here. It's almost the same as this one, the second identity, except here we have a plus and here we have a minus. So we have slight variation on the signs of the terms of the factors. And so that is our fourth identity um, that I will present. And so at this point, we'll go on to look at the fifth identity and the last identity. For the fifth identity, we have x power 4 plus 4 times y power 4 equals to this product here. So there is the factorization, I think it has a name. It's called so something like this. So it is called the Sophie Germain identity. So again, we can try to write out to prove it, you can try to write out the factors on the right hand side, and then you can expand as we have done previously to show that this has to be equal to the left hand side. But this time I'll try to move from the left hand side to the right hand side. So in this case, I have x power 4 plus 4 times y power 4. So in this case, I will try to utilize the first factorization and try to prove this identity. In which case, I will introduce another factor, which is 4x squared y squared, and then I will subtract it at the end. So I have added 4x squared y squared and subtracted 4x squared y squared. So this is valid. And then I will try to separate them. I will consider this factor separately from the last one. So for this factor, actually this is a squared of x squared plus 2y squared, like that. It's easy to verify because as we all know, a plus b squared is a squared plus 2ab plus b squared. Yeah. So in this case, when you expand this, you get x squared squared, which is x to the 4, times 2 times x squared times 2y squared is 4x squared y squared, and the square of this last term will be 4 times x to the y. So we have this term here, and for the other term, it also happens to be a square of this term here, 2x squared y squared. When you square this term here, you will get our last term on the first row. So again, in this case, we will try to invoke the first factorization identity, which is the difference of two squares. So in this case, you have the first term minus the second term, then the first term plus the second term. So in this case, it will be x squared plus 2y squared minus this term, which is 2xy, then we'll have x squared plus 2y squared plus 2xy. So this is precisely what we wanted to show on the fifth algebraic identity. Okay, so far we have seen algebraic identities for two variables. For this last example, which is, I believe, the most important one, is about three variables when you have x, y, and z. It says that the sum of the cubes of two, or the cubes of three, of three numbers, x, y, and z, minus 3 times x, y, z equals to the product of this term here and this factor here. So this is the sum of x, y, and z, and the sum of x squared plus y squared plus z squared minus xy minus yz minus zx. So again, you can try to expand this product here and we'll have a lot of cancellations as in the previous cases, and then at the end we'll have this sum here. And for this one, I will leave it to you as an exercise to actually try to prove that this product, when you expand it, you will end up at this identity. Okay, so this one you can try it yourself and you will see that there is a lot of cancellation going on. And so that concludes our first part of this.